I am Lakshmidhar Behera in Department of Electrical Engineering, IIT Kanpur. So, I will be teaching all of you intelligent control, and this will be an introductory lecture. This is a first lecture. In this introductory lecture, I would cover those aspects of intelligent control that will give you a holistic view or a complete picture of this subject. Why intelligent control? Why we should learn this topic? So, here is the outline. All those who will be looking forward to attending this lecture series, I assume that all of you have sufficient background on linear control system, and when we talk about intelligent control, most of the time we talk about the controlling nonlinear systems. This is one of the reason for studying intelligent control is that it is not so difficult to design linear control system, but it is difficult to design nonlinear control system. We will cover in this intelligent control course fuzzy logic, neural network, fuzzy neural. These are the tools. There are various tools actually for intelligent control techniques, but in this course we will limit our focus on these three things: fuzzy logic, neural network, fuzzy neural network. And today's introductory class, I will show you some of these typical examples where intelligent control is pretty nice. They are pretty interesting as well as exciting, also challenging. So, I just remind you what is linear system theory. You express the system model either using state space or using transfer function. Let me tell you that how do you design a control system. We have a plant. The plant may be a power system, plant may be a pH reactor, plant may be a robot manipulator, any physical device that is of interest to us, and we want to control that device. Controlling device means we regulate some of the variables that is of importance in this device, like maybe speed of a motor, or the pH value of a reactor, or voltage level in power system bus bar. So, there are various physical variables that we would like to govern or control. Before we can control, we must know the system as it is, the plant as it is. So, that is where we talk about mathematical model. So, once we derive a mathematical model, and these mathematical models are derived using the basic principles of science, whether it is physics, chemistry, biology, the physical laws that we have in these fields. Using these laws, like for example, if I am simply talking about the motor, the dynamic model of a motor, I must be very much clear about the principles by which a electromechanical device works. There is a mechanical principle, there is electrical principle combined together. So, these physical principles should be very clear to me before I can describe a physical device using mathematical model. So, these mathematical models, they can be of various type, but popularly they are either state space model or transfer function model. And the various, once you have a mathematical model, we do not again look at the physical system for designing control system. We design a control system for the physical model, for the mathematical model, and after designing a control system for the mathematical model that we have derived for a physical system, we test on the real system, our control algorithm. So, as far as the design is concerned, always we value the mathematical model of the system that has been derived, and these two categories, either state space or transfer function, that are very widely studied in literature, and most of our control systems are based on these two models, these two different models. And as far as the transfer functions are concerned, we normally, the industrial controllers, they normally you design PID controller either using frequency domain approach or time domain approach. All of you might have heard about root locus method, that is under time domain approach, using Bode plot, Nyquist diagram, this is frequency domain. And in state feedback controller, you must have heard about pole placement, linear quadratic regulator, this is an optimal control, and also robust controller, this is another type of controller when we assume these plant models are not exact, they are inexact. So, this is a kind of a overview of the linear systems, that is, we have state space model or transfer function model of an actual plant, and for these two models we design various type of controllers. For transfer function, we design PID controller or PID compensator using frequency domain or time domain approach, and for state feedback controller we design pole placement, linear quadratic regulator. And when models are not exact, there are certain uncertainties, we talk about robust controller. That means, if I design a controller for a particular plant with certain uncertainty, the mathematical model that is given to me, but that is little uncertain, then how robust is my control system in the presence of uncertainties. So, now the question is that the linear systems are very well understood most of the time in literature. From design principle wise, linear systems are well covered, but are systems linear? This is a very paramount question. Is our systems linear, the real system, physical system? Now, here is a simple familiar physical device you are looking here. This is mass, damper and spring system, and those all of you, I would expect that you have taken the control system course, and you must have studied this system in the beginning of a course. So, this is a popular second order model of this mx double dot plus bx dot plus kx equal to f. So, system is linear if b and k are constant coefficients, b and k constant coefficients, then the system is linear. But if these coefficients b and k have this following functional relationship, b1 x dot square is b and k1 x square is k, and we put these things here, the system becomes nonlinear. So, what I am suggesting you is that most of the time physical systems, although we model using linear system theory, but they are nonlinear, and there are also systems which are inherently nonlinear. I will take a special class on nonlinear system during this lecture series, but we will not talk much about this difference between linear and nonlinear. From the mathematical principle, we will discuss that as course progresses. But what I am trying to say is that most of the system we encounter, they are naturally nonlinear rather than linear. And for nonlinear systems, we have the researchers, the control engineers, they have developed various theories to tackle these kind of plants when the plant is nonlinear. So, there are certain popular control methodologies, you have not come across these kind of methodologies in linear system theory. These are known as feedback linearization, backstepping, sliding mode control, singular perturbation method, passivity based control. So, these are all various categories of nonlinear control methodologies. Of course, we will not be discussing in detail about nonlinear these kind of methodologies, but we will adopt this principle while designing intelligent control. So, in intelligent control is not something the concept wise, it is not something quite apart from what we are studying in linear control theory or nonlinear control theory. Rather, these concepts are taken very nicely, and in a very convenient manner they are put forth in such a way the control designs becomes very easy, and particularly you can adapt to any kind of plant. Okay. So, here is a limitation of nonlinear control strategies. Controller design is system specific. Normally, just like a linear system theory, for a generalized second order linear system, you can always have a generalized control law. Similarly, for a generalized nth order system, you can have a generalized control law. But controller designed for nonlinear system, you can't say there is some every nonlinear system has a different structure, and that is why we can't actually make a kind of a generalized control law for a nonlinear system within the domain of nonlinear control theory. So, that is why the controller design becomes system specific. We design a control system for a specific nonlinear plant with a specific nonlinear model. So, no generalized tool for analysis actually is present in nonlinear control theory. Also, whenever there is unstructured dynamics, then this theory may fail, that is, the stability may not be guaranteed. Also, when there are parametric uncertainties, unknown dynamics, we do not know how within the paradigm of nonlinear control theory they can be taken into account. Although we have certain methodologies to adopt robust control methodology, adaptive control methodology for nonlinear system to take some of these issues into account, but in general in a classical nonlinear control strategies are not so robust against unstructured dynamics, parametric uncertainties and unknown dynamics. So, that is why we are now talking about intelligent control. So, before we talk about intelligent control, is it that linear system theory is not intelligent? Is it that nonlinear control theory is not intelligence? It is. One may argue, yes, you need intelligence to design control system, whether it is a linear control theory or nonlinear control theory. But in this case, when we talk specifically intelligent control theory, the certain work in artificial intelligence, certain results in artificial intelligence that is motivated to understand intelligence has been used in the framework of intelligent control, and that is why we say intelligent control. That is, when we coin the word intelligence, intelligent control, some of these tools that we have worked in the field of artificial intelligence, like neural network, fuzzy logic, Petri nets, like that, when we use these tools in designing control system, then historically the field has been known as intelligent control. Now, what is intelligence? I would say something mysterious. Turing proposed it to be combination of 5 components, and you say that this is intelligence and it has 5 components: perception, problem solving, reasoning, learning, which is very important, particularly as far as this course is concerned. This is one of the most important component that we will be considering. Language understanding, of course, we will not be concerned much of this component of intelligence. But actually what is intelligence is very difficult to answer, but for the time being probably we can say, okay, these components, when they are there, probably they constitute together intelligence. Okay. Now we will talk about intelligence again. Normally the intuition that we have for using the term intelligence, it comes from the human way of doing things, human way of solving things. Normally we always ask a question, how we solve a problem, how we rotate our hand or rotate our head when we track a target, or when we want to pick a ball, how we move, or when we play a soccer in the football field, how do we give a pass or how do we intercept a football. So the human way of working is something that is very is very little known about it, and that's why when we talk about intelligence, we always try to understand how biological organisms function at specific situation. And when a machine can mimic the way the biological organism behave to situation, to environment, and then we say probably they are intelligent machine. So when I said here biologically plausible foundation to intelligent machine, so because I am saying biologically plausible foundation, when I say, so I coin here 3 particular terms: intelligently observe, intelligent prediction, intelligent interaction. Observation means we get certain data, and I used a filter and I have now faithful data, and using this data I want to make a model of the system. So this is called system identification. Why? Because once you have a model, you can predict about the system behavior. This is all control. How do we do control? So we observe and then predict, and finally intelligent interaction. Based on the model, I can predict various behavior, and according to the desired behavior, whatever my desired behavior, I do interaction. This is called adaptive control in classical term. So the basic foundation for an intelligent machine, when I talk about intelligently observe, intelligent prediction, intelligent interaction, the classical counterparts are stochastic filtering, system identification, and adaptive control. Now here, as I said here, real intelligence is what determines a normal thought process of a human. Artificial intelligence is a property of machines which gives it ability to mimic the human thought process. So the intelligent machines are developed based on intelligence of a subject, of a designer, of a person, of a human being. Now to question, can we construct a control system that hypothesize its own control law. Like, we encounter a plant, and looking at plant behavior, sometime we have to switch from one control system to another control system where the plant is operating. Plant is operating linear zone, nonlinear zone. Probably an operator can take a very nice intelligent decision about it, but can a machine do it? Can a machine actually hypothesize a control law looking at the model? Can we design a method that can estimate any signal embedded in a noise without assuming any signal or noise behavior? This is the first part. What I am trying to say is that before we model a system, we need to observe, that is, we are collecting certain data from the system, and how do we actually, and this data is polluted or corrupted by noise, how do we separate the actual data from the corrupted data? So, this is the second question. First question is that a control system can it be able to hypothesize its own control law? These are very important questions we should think actually. Now, let me give you a simple example. What you are seeing is actually a second order nonlinear system. This is h y is a nonlinear function, g y is another nonlinear function, and if we actually want to study the stability of this type of function, then if given that h y is greater than 0, always it is positive, implying, then the stability analysis we do using Lyapunov stability theory. But unfortunately, in Lyapunov stability theory, it is the person who is actually analyzing, he has to hypothesize what must be a valid Lyapunov function. And here you see we have a Lyapunov function Vx 0 to x1, this is the function g, different integrated function g over from 0 to x1 and plus half x2 square, where you convert this nonlinear system into state space model where two states are y and y dot, x1 and x2. So, then this becomes a valid Lyapunov function, and you can see that using this Lyapunov function you can always say whether the system is stable or not stable. But can we construct an intelligent network or intelligent machine that can hypothesize the above Lyapunov function? That is, given a nonlinear function, can the machine come up with its own hypothesis that this is going to be right Lyapunov function for this system? If we can, probably we can say that we have an intelligent network or intelligent machine here sitting right in front of us. We do not have to think, my machine can actually predict a proper Lyapunov function for any system. Of course, Lyapunov function is always most of the time it is always defined for nonlinear system, because for linear system the form of Lyapunov function is already known, but for nonlinear system Lyapunov function is system specific, it is not known. This example, like this is a typical control law for a linear system. We normally define, and this typical control law, this structure, the control structure is valid for any linear system, whether we design a state feedback controller linear quadratic regulator and so forth. So, as I said earlier, can that because we know based on our experience, we know this is a generic structure of a control law for a linear system, but and how do we know this? So, how does the control engineer know that such a control law will help? It is through his experience, intuition, and some mathematics that he has learnt. So, based on that, the moment I look at a linear system, I can always say this is the generic form of control law, state feedback control law. But can a learning machine do so? This is the question. If I am actually doing intelligent control, I am trying to learn intelligent control, can I say that this is the machine that I have designed, it goes through the data from the system, and then he says this is going to be a generic control law for this system. Can we predict, or can my machine predict? This is again the same thing that I said. When I have a signal, the signal can be a DC time independent, sinusoid, modulated, various types of signals I can have, and these signals are corrupted with noise, and I want to separate the signal from the corrupted signal. So, when I want to estimate the corruption or the noise that has been injected into the signal, may be Gaussian, non-Gaussian, and so many things, and then with all these assumptions, that means in classical approach what I say when I try to separate a signal from its corrupted counterpart, then I always assume what kind of signal it can be. I assume what kind of noise it can be. I always take these models into account, and then I propose an estimator. So, but in general, but can we say this kind of methodology is intelligent? This is a question. The question is that we have to make so many assumptions before we make a predictive model. So, what I said until now is that I just raised certain issues in your mind about intelligent control. What is intelligence? Why we need intelligent control? So, here we can summarize it saying the topic is why intelligent control. So, first is it should take care of model uncertainties, that is when we derive mathematical model of any nonlinear plant, the model is not always exact. So, there are always associated uncertainties. Second, my control system should be adaptive to change in environment, okay, and also it should be distributed in nature. So, here let us ask this question, that where we are really would like to use this kind of methodology. So, one of the very typical situation is unmanned vehicle, not only the flying one, even our we can design a laboratory size automobile which where the driver is a machine instead of a human being. Also here you can see that a robot playing squash, or even robot can also play soccer. Here is a you see the robotic gripper picking a delicate substance like in an egg. This is another kind of robot gripper. So, there can be many varieties of sophisticated machines in applications like healthcare, mine exploration detection, security, the surveillance monitoring, industrial cleaning and so forth. Even here you can see robotic surgery. These all require, these are all activities that requires expertise, and an expert, a human expert does these things very well. So, can we replace these human experts by intelligent machine? This is one of the questions that we always ask when we talk about intelligent control. So, by saying that what we are going to do with intelligent control, it is not that intelligent control completely rejects the methodologies that we have learnt in control theory, linear control theory, nonlinear control theory. It also it does not reject, it also uses even conventional control methods. And we can also, these conventional control schemes can be very nicely or adaptively coupled in specific situation, which normally we call switching control using intelligent control techniques. Okay. So, here some of the definition of level of intelligence. At the lowest level, we have to sense the environment, like I want to do a temperature control, I must have temperature sensor. I want to do position control, I have to have a position sensor. Then higher level of intelligence, this is ability to recognize object and event, like a robot should be able to recognize where is the ball if it wants to play the soccer. If surgery, when a robotic surgery is taking place, the robot there should be able to identify each and every organ of the human body. Similarly, also to represent knowledge in a world model, the way we manipulate the objects in this world. And of course, the advances, of course, this is a very high level of intelligence that we even do not understand, the capacity to perceive and understand. I will talk this at the end of this lecture today. Okay. So, let us be a little speedy here, because I wanted to give you a little feel of this entire subject today in this introductory class. So, here are certain various methodologies that we adopt while designing intelligent control system. Automata theory we use, hybrid system concept, Petri nets, neural networks, fuzzy logic, evolution algorithm. But basically we will mostly focus this last three tools, because they have become very popular in designing intelligent control theory. Okay. So, what is fuzzy logic? Some of the time, most of the time, people are fascinated about fuzzy logic controller. At some point of time in Japan, the scientists designed fuzzy logic controller for even a very any kind of household appliances, like like even whether it is a room heater, it is a washing machine. So, its popularity is that it has been applied to various engineering products. But in this lecture we will, in the lecture series we will discuss detail what is fuzzy logic. Today I will not talk in detail, I will just let you know what is exactly little idea about fuzzy logic. You see that this is this is a line, and in this line you have 0, 1, 2, 3 and this -1, -2, -3. So, when I say 0, it is 0. Thus, if it is 0, then I say it is 0, its truth value is 1, and if it is not 0, its truth value is 0. But the moment I say almost 0, then I can think of a picture like this, that between almost like minus 1 to 1, the values around 0 is 0, because this is almost 0, and you can see that this gradient allows me to allow maximum weightage of the value very near to 0, and as the value goes away from 0, the truth value reduces. So, we are discussing concept of a fuzzy number. We talked about 0, almost 0. This is a, I am not very precise, but that is the way I use my day to day language in interpreting the real world. And when I say near 0, maybe the bandwidth of this triangle represents actually the truth value. Okay. So, you can see that this is more, bandwidth increases near 0. So, this is the concept of fuzzy number. I can I'll give little explanation. Okay, as we discuss specifically fuzzy logic controller aspect in this course, we will discuss more detail about this concept. For the moment, let me tell you that when I say fuzzy logic, that is the variables that we encounter in physical devices, I use the fuzzy number to describe these variables, and using this methodology when I design a controller, I say it is a fuzzy logic controller. Now, it is neural network. Neural networks are basically inspired by various way of observing the biological organism. The most the time it is motivated from human way of learning. It is a learning theory. So, this is an artificial network that learns from example, and because it is distributed in nature, fault tolerant, parallel processing of data, distributed structure. This is the neural network that we normally design, but if you look at actual neuron, the biological neuron, they are highly complex unit with the information contained in spikes. Computation and plasticity exhibited at an advanced level. Information processing is done through complex processes and not simple aggregation. But when we talk about artificial neural network, neurons are elementary units, can be digital, analog. We can also make some spike models. There are basic computation, summation, multiplication, and here is a very simple McCulloch-Pitts neuron model. Here your inputs, and these are all synaptic weights, they are all summed here, and then there is an activation function, and here is your output y. So, in a way your output is summation of the signal multiplied with synaptic weight over many input channels. So, you can see that how this is a specific neuron, this is action, through action this neuron actuates a signal, and this signals fans out through synapses to various neurons. Okay. So, similarly, this is a biological neuron, and here it is a classical artificial neuron, and you can see this is a computational unit, and there are many inputs reaching this, just like here this is one input, another input, another input, another input. This input excites this neuron. Similarly, there are many inputs that excite this computational unit, and the output again excites many other units, just like here. And like that, taking certain concepts in actual neural network, we develop these artificial computing model having similar structure. Although we do that, let us try to see what is exactly we are up to. It is a brain, and you see that in this brain there are various location, this is auditory, this is visual cortex. So, there are various locations where various functions take place in the brain. If you look at a computer and the brain, this is a central processing unit, and a brain, let us compare what is the connection between our high speed computers that are available in the market today and a brain. Approximately there are 10 to the power 14 synapses in the human brain, 10 to the power 14, whereas typically you will have 10 to the power 8 transistors inside a CPU. The element size almost comparable, both the things 10 to the power minus 6, and energy use is almost like 30 watt and comparable actually, that is the energy dissipated in a brain almost and in a computer. But you see the processing speed is only 100 hertz, very slow our brain is, whereas computer nowadays some gigahertz. And when you compare this, you get an idea that although the computer is very fast that we have, but it is very slow to do intelligent tasks like pattern recognition, language understanding. These are certain activities humans do much better, but with such a slow speed, 100 hertz. So, little contrasting, you will see that between these two, the difference is that one of the very big difference between these two structure, one is brain, another is central processing unit, is that the brain, it learns, we learn, okay. There is certain mapping that forms in biological brain that we have studied neuroscience, that is not there in a central processing unit. And of course, this we do not know whether the self awareness takes place in the brain or somewhere else, but of course we know that in a computer there is no self awareness. Saying that, let us what we will be discovering in this course. We will be covering, when we discuss neural network, we will be covering some of the popular learning methods, because neural networks are analogous to adaptive control concepts that we have in control theory. And one of the most important aspect of intelligent control is to learn the control parameters, to learn the system model. So, some of the learning methodologies we will be learning here: the backpropagation algorithm, real time learning algorithm for recurrent network, Cohen self organizing feature map, Hopfield network. If time permits, we may also discuss about support vector machine. Okay, so these are all, as I have already said, these are all summary of neural network. We will discuss these concepts even in more rigorous manner in the next class. Okay. Some of the applications that we will rigorously take up in this course is we will show how to design a fuzzy logic controller. So, let me summarize now what we talked about. We talked about fuzzy logic controller, fuzzy logic, neural network. We did not talk so much about evolutionary computation. This also we will talk as we take that specific subject. And here under fuzzy logic controller, when we teach through this course, when we learn through this course, these are some of the interesting physical devices that we will consider for designing. One is single link manipulator. We will take a very simple system so that we can design completely, we will simulate it. Sometimes also I will show you some of the experimental results, like inertial wheel pendulum. This is in my lab, and my students who are working on this particular system, they have certain nice interesting results, and I will demonstrate that also in this course. So, inertial wheel pendulum, pH reactor, single link manipulator, these are very nice interesting nonlinear systems, and very interesting to see that how we can design controller using fuzzy logic concepts. So, this is a little details a single link manipulator has, you see that because of the sin theta term, the system becomes nonlinear, it does not follow the superposition principle. We will be designing these all varieties of controller, PID controller, fuzzy logic controller, we will use also genetic algorithm how to optimize fuzzy logic controller. So, these are the the insight, the description of the course model that I am now making, so that you are very well aware that what we are going to cover in this course. And here is a pH controller. You can see is that this is a continuously stirred tank reactor, and here there are three things entering into this particular container, that is buffer is a substance, and then acid as well as base. These are various kinds of liquids that enters into this this container based on their pH value. And the objective is that we want to maintain the pH of this container constant. And so, what we normally do is that we control only the base flow, means from the plant wastage or something like that, the various things enter into this, and this waste product has to be discharged to the environment. But if it is too its pH value is towards acidity, is more likely acidic or more likely alkaline, accordingly this will have a very drastic impact on the environment. To avoid that, we want to neutralize the pH value. Normally the neutralized value of pH is 7, and so how do we inject either base or acid into the system such that this pH remains constant. Although this looks like a very simple system, but the dynamics becomes nonlinear. We will show in detail how to solve this control system design for this system. Actually, this is a practical system we have already done. We have synthesized a pH reactor, and we have actually applied fuzzy logic controller to this pH reactor in detail. So, this we will take in detail. Here is you can see that inertial wheel pendulum, and you can see that this what you are seeing here is the inverter, the pendulum attached with a disc here. So, this is a pendulum rod, and that there is a disc. So, the objective is to bring this pendulum to the top position, and that is done using certain concepts of nonlinear control, we say swing up control and balancing control. This we will discuss in detail, and we will show that how we can design for this also fuzzy logic controller. The other controllers that we will be designing and we will demonstrate in terms of the application of neural network. Here are certain systems that we will discuss in this course. One is robot arm, visual motor coordination. This is hand eye coordination, just like when I pass a ball to my fellow player, there is enough coordination takes place between hand, leg and eye. Similarly, when I try to exhibit any skill with my hand, then for manipulating certain environment around me, then there is also certain degree of coordination between hand and eye. So, this is called visual motor coordination, and we will solve this problem using neural controller. Similarly, binocular vision system for object tracking. This is a typical robot manipulator. You can see this is a gripper, and these are the one link, another link, and this is a base. So, this is a typical this is a dynamics of this robot manipulator, and this is a binocular vision system. You have two robot camera, sorry, this is two camera, and these two camera are tracking certain moving object. This is a pan. This pan can move upward, downward in certain angle, and accordingly this also this camera here and here, they can also turn in a circle. So, as per that we can actually see this camera is looking at a point here. This is the point P, and this is the trajectory of my moving object. This is the trajectory of my moving object, and as the object moves, I want to focus the object as it moves. And how do I exactly orient towards the object? So, this is called a binocular vision system. This is called visual navigation also. So, we will also discuss this kind of problem, and we would like to solve using neural network. Okay. So, what I gave you today is that what we are going to learn in this not, of course, we did not tell in detail what we are going to learn, just highlighted some of the things that we are going to learn in this course, intelligent control. So, while saying that, let me conclude this lecture in a little philosophical manner, saying, because we talked about intelligent control, but after learning this course or taking this course, probably we may still inquire about what is after all the intelligence. So, the big question is, all the methods discussed so far make strong assumption about the space around. That is, when we use, whether it is neural network or fuzzy logic or Cohen and Shum, any method that have been adopted in intelligent control framework, so they all make always many strong assumptions, and normally they cannot work in a generalized condition. And the question is that they can they hypothesize a theory. When I design all this controller, I always take the data, the engineer takes the data, he always builds these models that that are updated. They update their own weights based on the feedback from the plant, but the structure of the controller, the model that we by which we assume the physical plant, all these are done by the engineer, and also the structure of the intelligent controller is also decided by the engineer. But we do not have a machine that can hypothesize everything. The model it should select, the controller it should select looking at simply data, that as it encounters a specific kind of data from a plant, can it come up with a specific controller architecture and can come up with specific type of system model. That is the question that we are asking now. Similarly, because we are talking about learning systems in this course, we will be talking a lot about it. Again, we can ask the question that can a learning theory prove a theorem? Can it propose a theory similar to special theory of relativity, like can it become an artificial Einstein? So, like that we can always become a little philosophical when we actually try to understand the import of the word intelligence. So, finally, can we bring a machine or system close to human way of operation, not his behavior. And you will see that the entire course that we will be discussing various tools, they only will be dealing with these two things, behavior, that these tools are actually developed while mimicking the human behavior, but not the human way of working. An intelligent machine is one which learns and thinks and behaves in line with the thought process that we would like, but we will be very far from it. At least at the moment, we are very far from this target of achieving real intelligence. So, finally, I would like to tell you a very important aspect of intelligence is perception. That probably, this, why I am saying is that as you will go through this particular course, you will see that we will not be addressing this issue, but these are the issues that makes the concept of intelligence very exciting. So, what I am talking here about the role of perception. So, we showed a brain, and in that brain, so you just look at this brain, the various location of this brain, we have visual cortex, we have auditory cortex, we have various location in this brain, and they perform various actions, and this is already has been these things we have already verified using various studies in neuroscience, and these studies, you can say anatomical and neurophysiological evidence, neuropsychological evidence, brain imaging. These are various methods by which we know that various parts of brain, they function, they do various different functions. But when we have a perception of the world, we have a unique perception, that is, how do we experience a coherent world, that whenever I perceive, I do not perceive that my visual cortex is processing vision or color, and my auditory cortex is processing sound and so forth. We do not. We perceive my environment in a very unique way, in a coherent manner. So, this is called unity of perception, and intelligence has also something to do with this unity of perception, awareness, and obviously certain things are not very clear to us until now, but nonetheless still you will see that this intelligent control course will be very interesting, because some of the new concepts we can learn about them, and we will learn that how to apply these new concepts like neural network, fuzzy logic, fuzzy neural network, genetic algorithm, how to apply these principles in control theory. Thank you very much.